Canada's freezing winters present a unique opportunity to harness natural cold for sustainable cooling. Traditional cooling systems are energy-intensive and contribute to high costs and greenhouse gas emissions. Our project leverages the concept of ice thermal energy storage, using winter temperatures to freeze water, which then provides cooling in summer. This method is renewable, cost-effective, and reduces reliance on conventional air conditioning. By combining solar power with thermal storage, we aim to create an eco-friendly solution.
Our goal is to design and build an ice thermal energy storage system that provides efficient cooling for indoor spaces. The system freezes water in winter using ambient cold, stores the ice in an insulated tank, and uses it to cool air in summer. Key components include solar panels, an Arduino Uno for control, temperature sensors, and a heat exchanger with copper tubes. This project aligns with sustainability goals by minimizing energy use and eliminating refrigerants.
Here's our prototype in action, a compact, self-contained cooling system. The core is an insulated aluminum tank with 16 copper tubes inside for efficient ice formation and heat transfer. We've wrapped the entire unit in thick foam insulation to lock in the cold. Up top, you'll see the small solar panel powering our Arduino control system, which manages the cooling fans and dampers on this side. The product includes this clear plywood test space where we can simulate room conditions and demonstrate the cooling effect. Every component is designed for efficiency and easy scaling to full-size applications. Here's a look at the system design. The aluminum tank stores ice, while copper tubes facilitate heat transfer. Double-layered insulation ensures minimal thermal loss. The solar panel powers the Arduino, which controls fans and monitors temperature. This schematic highlights how cold air flows through the system, cooling indoor spaces efficiently.
We're using 16 copper tubes to maximize surface area for efficient heat transfer. Now drilling the aluminum sheets, these 5/8" holes will hold our copper tubes in perfect alignment for optimal thermal contact. Cutting and shaping the heat exchanger walls, notice the flat end surface that will ensure that no water will be leaking. Sliding the copper tubes into place, this interlocking design creates a continuous thermal pathway without any weak points. All sides feature 1-inch styroboard insulation rated ART5, that's 5 square meter Kelvin per watt. We've completely encased the heat exchanger, including custom form sections for the fan reducer. Each panel is secured with heavy-duty aluminum tape, chosen for its superior thermal sealing and moisture resistance. The tape's reflective surface also minimizes radiant heat transfer, while the overlapping seams create a perfect vapor barrier.
The styroboard reducer slides onto the heat exchanger. The DC fan presses firmly into its slot. The vent connects to the reducer. We apply full-width aluminum tape around the joint. The connection is now airtight. Now, we are ready for the electrical works.
The solar panel and 12-volt battery terminate at the charge controller. A 12V line powers the fans, while a buck converter steps down to 5 volts for the Arduino, LCD, sensors, servo, and data logger. Wind velocity was measured with a thermal anemometer, while solar irradiance data was collected using a solar analyzer. The system operates in 2 modes: freezing, charging, and cooling, discharging. In charging mode, outdoor air flows through the copper tubes via intake and exhaust openings, extracting heat from the water to form ice inside the heat exchanger. In cooling mode, warm indoor air is drawn through the ice-filled copper tubes. The phase change from ice to water absorbs the heat, cooling the air in effect. This provides refrigerant-free cooling until all ice is depleted. Room temperature dropped from 45 degrees Celsius to 21 degrees Celsius, supply air cooled in sync, and outside air stayed stable, proving the system effectively managed indoor cooling. All 3 fans stayed on during cooling, ensuring steady airflow and efficient temperature drop. Here's the data gathered during the simulation testing.
Our ice thermal energy storage system isn't just a prototype, it's a blueprint for the future. With 30% lower energy costs versus conventional cooling, 0 refrigerants to harm the environment, solar-powered sustainability and scalability for homes, industries, and cities. By storing winter's cold energy, we're reducing summer's energy demand. Join us in cooling the planet sustainably. Cooling our home, one ice block at a time. Thank you.